try counting to infinity. Go ahead. Start now. 1, 2, 3. You will die before you reach 1,000,000. Your species will go extinct before you reach 1,000,000,000,000. The sun will burn out, the stars will fade, and the universe will grow cold and dark while you're still counting. And you will not be 1% of the way there. Because infinity has no percentage. It has no halfway point. It has no end. Scientists have confirmed that the universe may actually be infinite. Not metaphorically, not poetically, physically infinite, stretching forever in every direction without boundary, edge, or wall. Your brain evolved to track gazelles across African savannas. It was never designed to comprehend something that has no finish line. If you want to understand why infinity breaks human minds, hit that like button and subscribe. Let's begin. Your ancestors never needed to count beyond the number of fingers on their hands. For 300,000 years of human existence, the largest quantities that mattered were the number of predators stalking the tall grass, the number of days until the rainy season, or the number of tribe members sharing a fire. Evolution sculpted human brains to handle these manageable numbers with remarkable efficiency. Anything beyond a few thousand served no survival purpose. A hunter tracking a herd of antelope needed to know whether he faced 5 animals or 50. He never needed to distinguish between 5 million and 50 million. And so our neural machinery was never upgraded to process quantities beyond immediate practical relevance. It was certainly never designed to contemplate the infinite. This is not a metaphor or philosophical speculation. Cognitive scientists have confirmed through decades of rigorous experimentation that human brains possess what researchers call the approximate number system. This mental toolkit allows rapid estimation of quantities without precise counting. You can glance at a handful of berries scattered across a forest floor and know instantly whether there are 5 or 50 without counting each one individually. This ability proved extraordinarily useful for survival. Quick numerical assessment meant the difference between pursuing a worthwhile food source and wasting energy on meager rewards. But this system breaks down dramatically as numbers grow larger. Show someone 2 photographs, one containing 900 dots and another containing 1,000 dots, and most people cannot reliably tell which image has more without laboriously counting each dot individually. The approximate number system that works beautifully for small quantities becomes hopelessly imprecise at larger scales. The ratio between 900 and 1,000 is too close for our evolved intuitions to distinguish. The failure intensifies catastrophically at even larger scales. Scientists conducted experiments where participants were asked to place numbers on a line stretching from 0 to 1 billion. The task seems straightforward. Just mark where 1 million should appear on that line. Most adults placed 1 million roughly halfway between 0 and 1 billion. This is catastrophically wrong. 1 million is 1,000th of the way to 1 billion. The correct placement would be virtually indistinguishable from 0 itself. If you placed 1 million at the correct location on a meter-long line representing 0 to 1 billion, your mark would sit just 1 millimeter from the 0 point. Our brains compress large numbers logarithmically, meaning we perceive the jump from 1 to 10 as psychologically similar to the jump from 1 million to 10 million, even though the second jump involves 9 million more units than the first. This compression distorts our intuitive sense of magnitude in ways that become problematic when precision matters. This logarithmic compression served our ancestors remarkably well in the environments where human cognition evolved. Whether facing 3 lions or 30 lions made little practical difference for survival strategy. Either way, running was the correct response. The neural resources required to precisely distinguish between these quantities would have been wasted computational overhead. Evolution optimized for speed and efficiency rather than precision, at scales that did not matter. But this same mental architecture fails spectacularly when we attempt to comprehend cosmic scales, where the difference between millions and billions and trillions actually matters enormously. A policy that costs $1 million and a policy that costs $1 billion differ by a factor of 1,000. Yet our intuitions treat them as vaguely similar large numbers rather than quantities separated by 3 orders of magnitude. Consider the challenge of visualizing 1 trillion. If you counted 1 number per second without sleeping, eating, or resting for even a moment, reaching 1 trillion would require 31,700 years of continuous counting. You would begin counting when Neanderthals still walked the earth alongside our ancestors. You would continue counting through the agricultural revolution that transformed human societies from nomadic hunters to settled farmers. You would count through the rise and fall of every empire in human history, through the development of writing and mathematics, through the Industrial Revolution, the space age, and whatever technological transformations come next. You would keep counting long after human civilization transforms beyond recognition or perhaps ceases to exist entirely. And at the end of this unimaginable marathon, spanning longer than human civilization has existed, you would have counted to a number that astronomers use casually when discussing star populations and galaxy clusters. 1 trillion is routine for cosmologists. For human intuition, it is incomprehensible. But 1 trillion is nothing compared to infinity. The word infinity derives from the Latin infinitus, meaning boundlessness or endlessness. Unlike 1 trillion, infinity is not a very large number. It is not a number at all in the conventional sense. Infinity represents a quantity that surpasses every finite number you could ever name. No matter how large a number you write down, no matter how many zeros you append, infinity remains larger. This is not a difference of degree like the difference between 1,000 and 1 million. It is a difference of kind, a fundamentally different category of quantity. Think about what this means. Take any number you can imagine, add 1 trillion to it. Infinity is still larger. Multiply your number by itself 1 trillion times. Infinity remains larger. Raise your number to the power of itself, raise to the power of itself. Repeat it until you run out of patience or paper or lifetime. Infinity still exceeds your result. No finite operation performed on finite numbers can ever reach infinity, because infinity is not on the same number line as the quantities you manipulate. Ancient civilizations grappled with this concept long before modern mathematics formalized it. Greek philosophers engaged in heated debates about whether the universe extended infinitely or ended at some cosmic boundary. The question seemed urgent because both answers led to profound difficulties. If the universe ended, what lay beyond its edge? If the universe was infinite, how could an actually infinite thing exist? Aristotle distinguished between potential infinity and actual infinity in a framework that influenced Western thought for 2 millennia. Potential infinity meant a process that could continue indefinitely without ever completing. You could always add 1 more to any number, generating an endless sequence without ever reaching a final infinite quantity. Aristotle accepted this kind of infinity as unproblematic. Actual infinity meant a completed infinite quantity existing all at once, and Aristotle rejected this as philosophically incoherent. The mathematician Georg Cantor revolutionized our understanding of infinity in the 19th century by proving through rigorous logic that infinity comes in different sizes. This discovery initially seems impossible, a contradiction in terms. How can one infinity be larger than another if both are infinite? Cantor demonstrated through elegant mathematical proof that while the infinity of counting numbers and the infinity of fractions are the same size, the infinity of real numbers between 0 and 1 is demonstrably larger than both. Cantor called this larger infinity the continuum and showed that infinitely many levels of infinity exist, each larger than the last, forming an endless hierarchy of infinite magnitudes. There is no largest infinity because whatever infinity you name, Cantor's techniques can construct a larger one. The mathematics is airtight, confirmed by over a century of mathematical verification. And yet the concept violates every intuition our brains possess about quantity and size. This mathematical framework reveals precisely why human intuition fails so completely when confronting infinity. We evolved to track discrete objects, countable things like predators or food sources or tribe members. The concept of multiple infinities of different sizes violates every assumption our brains make about how quantity works. It is like discovering that some forevers are longer than other forevers, that some endlessnesses are more endless than other endlessnesses. The psychological phenomenon called scope insensitivity compounds these difficulties in ways that affect not just mathematics, but moral reasoning and policy decisions. Studies consistently show that people donate roughly similar amounts of money to save 2,000 birds from oil spills or 200,000 birds from the same disaster. The emotional response does not scale with the numbers involved. Our empathy circuits saturate quickly, leaving us numb to quantities beyond immediate experience. Researchers presented subjects with donation requests framed around saving children's lives in carefully controlled experiments. Saving one child's life with a photograph and name elicited strong emotional and financial responses. People opened their wallets readily to help this specific, identifiable child. Saving 8 children described statistically produced measurably weaker responses. Saving millions of children through abstract policy interventions generated the weakest response of all, despite representing the largest potential impact by far. This scope insensitivity reflects genuine cognitive limitations rather than moral failure. Our ancestors evolved in small groups where every individual mattered personally. The neural circuits that generate empathy and moral concern develop to handle relationships with perhaps 150 other individuals, the estimated maximum size of stable human social groups. These circuits were never designed to process the suffering of millions, let alone respond proportionally to quantities approaching infinity. The implications for understanding cosmic infinity are profound and troubling. When astronomers tell us the universe may contain 2 trillion galaxies, each harboring hundreds of billions of stars, most people nod politely and move on with their days. The numbers are too large to trigger appropriate awe or existential reflection. When cosmologists suggest the universe may extend infinitely beyond our observable horizon, the claim feels more like poetry than physics, more like metaphor than measurement. Our brains lack the emotional circuitry to register what infinite really means in physical terms. The word infinite washes over consciousness like any other adjective without triggering the vertigo that would be appropriate if we truly comprehended its implications. This cognitive barrier has practical consequences extending far beyond abstract cosmology. Climate scientists struggle desperately to convey the difference between emissions measured in billions of tons versus trillions of tons. Both quantities feel equally abstract and enormous to audiences whose intuitions cannot distinguish between them. Epidemiologists found that urgent warnings about exponential viral growth, dismissed by politicians and publics who could not intuitively grasp what doubling meant over many cycles. Nuclear physicists working on the Manhattan Project reportedly struggled to communicate just how different nuclear weapons would be from conventional explosives, because the yield differences exceeded normal human comprehension. A bomb that explodes with the force of 20,000 tons of TNT is not 20,000 times worse than a 1-ton bomb in any way that human intuition can process. The jump is too large, the numbers too abstract, the comparison too removed from everyday experience. Neuroscientists have identified specific brain regions involved in numerical processing. The intraparietal sulcus, a region in the parietal lobe of the cortex, shows strong activation when people estimate quantities or compare numbers. Brain imaging studies reveal this region lighting up during numerical tasks across many different cultures and contexts, but this region developed for ancestral tasks involving manageable numbers, quantities relevant to survival on African savannas where numerical precision beyond a few hundred served no purpose. When asked to contemplate genuinely large numbers, brain imaging shows increased activity in areas associated with abstract reasoning rather than numerical intuition. We are literally using different mental tools to think about infinity, tools that were not designed for this purpose. The prefrontal cortex, associated with abstract thinking and logical reasoning, takes over from the intraparietal sulcus when numbers grow too large for intuitive processing. This neural transition reveals something important about infinity. When we contemplate infinite quantities, we are not really comprehending them in any meaningful sense. We are manipulating symbols according to logical rules, performing abstract operations that our prefrontal cortex can execute without genuine understanding. The mathematics works, the equations balance, but no one actually visualizes what the symbols represent. Philosophers have long debated whether infinity exists as anything more than a mathematical abstraction. Does physical infinity actually exist in the external world, or is it merely a useful concept for equations and proofs? This question gains urgent relevance when modern cosmology suggests we may inhabit a literally infinite universe. If infinity is just mathematical convenience, a mental tool for handling calculations that would otherwise be unmanageable, then the physical universe must be finite, however large it might be. If infinity can be physically real, then existence may extend without boundary in space, time, and perhaps other dimensions we cannot perceive. The theologian and philosopher Blaise Pascal captured the existential vertigo of contemplating infinity in his famous Pensées. Written in the 17th century as the scientific revolution was reshaping human understanding of cosmic scales. He wrote of the eternal silence of these infinite spaces that terrified him. Pascal was contemplating the emerging scientific worldview where Earth shrank from cosmic center to tiny speck orbiting an ordinary star. Modern astronomy has pushed this displacement even further than Pascal could have imagined. We are not just small compared to the cosmos. We may be infinitesimally small, occupying exactly 0% of an infinite universe. Not approximately zero, mathematically precisely zero. Any finite quantity divided by infinity equals zero. And human existence represents a finite quantity however you measure it. Children sometimes ask where the universe ends. Parents typically respond with some version of "it just keeps going," which technically may be correct according to current cosmological evidence, but does nothing to resolve the conceptual difficulty the child experiences. The child correctly intuits that everything they have ever encountered has boundaries. Rooms have walls, countries have borders, yards have fences, even the ocean stops at the shore. The idea of something with no boundary at all violates deep assumptions about how reality works. These intuitions trace back to our embodied experience as physical beings moving through bounded spaces. We move through the world by traveling from point to point. Every journey has a starting location and a destination. The concept of a journey through infinite space, where no matter how far you travel, infinite distance remains ahead of you, feels more like a nightmare than a physical possibility. And yet cosmological evidence increasingly suggests this nightmare accurately describes our actual situation. The ancient Greek philosopher Archytas of Tarentum proposed a thought experiment around 400 years before the Common Era that still challenges intuition today. Imagine traveling to the supposed edge of the universe. When you arrive at this boundary, could you extend your arm beyond it? If yes, then the boundary was not truly the edge, because space exists beyond it for your arm to occupy. If no, then what stops your arm? What substance or force prevents motion beyond this point? Either answer leads to contradictions for a finite bounded universe. This reasoning pushed many ancient thinkers toward accepting infinite spatial extent, despite its conceptual difficulties. A finite universe with an edge seemed even more paradoxical than an infinite universe without one. Modern physics offers no easy escape from these ancient paradoxes. Einstein's general relativity permits various cosmic geometries, some finite and some infinite. A positively curved universe could be finite yet unbounded, wrapping back on itself like the surface of a sphere where traveling in any direction eventually returns you to your starting point. This elegant solution avoids the problem of edges while maintaining finite volume, but current measurements of cosmic curvature suggest we live in a geometrically flat universe that could extend infinitely in all directions. Space appears flat to within measurement precision, and flat geometry is consistent with infinite extent. The observable universe, with its 93 billion light-year diameter, may represent merely a tiny bubble of visibility within an infinite cosmic ocean that extends forever in every direction. This possibility means that beyond your observational horizon lies not a wall or boundary, but simply more universe. And beyond that additional universe, more universe still. The pattern continues forever without termination, without edge, without any point where space stops and something else begins. Every point in an infinite universe is surrounded by infinite additional space, stretching toward infinity in every direction, simultaneously. Try to hold this concept in your mind for a moment. Feel your brain resist it. Notice how the idea keeps slipping away, replaced by assumptions of eventual boundary or ultimate edge. You imagine traveling outward until finally you reach somewhere different, somewhere that marks the end. This resistance is not intellectual failure or insufficient effort. It is your evolved neural architecture operating exactly as designed, optimized for finite African savannas, utterly incapable of containing the boundless. Human beings have invented mathematical notation specifically to handle these concepts without requiring intuitive comprehension. The infinity symbol, developed by mathematician John Wallis in the 17th century, allows calculations involving infinite quantities without requiring anyone to actually visualize what infinity means. This symbol, resembling a figure eight turned on its side, permits manipulation of infinite quantities through formal rules without demanding genuine understanding. This mathematical abstraction has proven remarkably powerful, enabling modern physics and engineering despite our cognitive limitations. Calculus, which forms the foundation of modern science, fundamentally involves limits approaching infinity. Engineers routinely calculate with infinite series and infinite sums. Physicists write equations where infinite quantities appear as natural components. All of this mathematics works, producing predictions that match experimental results to extraordinary precision. But there is something deeply troubling about a species that can write equations involving infinity while remaining fundamentally incapable of understanding what those equations describe. We are using tools more powerful than our minds can grasp. We are probing realities that exceed our cognitive horizons. And the answers coming back from those probes suggest that infinity may not be just mathematical convenience, but physical fact describing the actual structure of the cosmos. The universe we inhabit may literally never end. Space may extend forever in every direction. Time may stretch infinitely into both past and future. Certain physical quantities may actually reach infinite values in extreme conditions like the centers of black holes. Our brains evolved for a world of finite resources, countable threats, and bounded territories. And now those same brains are discovering that they exist within something genuinely infinite. This discovery does not upgrade our cognitive limitations. We remain the same evolved primates with the same approximate number systems and the same scope in sensitivity. The neurons in your head are the same neurons that helped your distant ancestors count berries and track predators. These neurons have not been redesigned for cosmic contemplation. The difference is that we now know what we cannot comprehend. We have discovered the walls of our own mental prison and found they cannot contain the reality we inhabit. Some philosophers find this situation humbling, a reminder of human cognitive limitations that should inspire epistemic humility about all our beliefs. Others find it terrifying, evidence that we exist in a cosmos fundamentally beyond our comprehension, whose true nature we can never understand. A few find it exhilarating, viewing the gap between human cognition and cosmic reality as an infinite frontier for exploration and discovery. But virtually everyone who seriously contemplates physical infinity experiences the same fundamental sensation at some point in their reflection. A kind of cognitive vertigo, a mental equivalent of standing at the edge of an infinite cliff and feeling the ground give way beneath assumptions that once seemed solid. The mind reaches for infinity, fails to grasp it, and falls backward into confusion and wonder. Your brain was never meant to process this. Natural selection did not design your neurons to contemplate the boundless. And yet, here you are, reading words about a concept that exceeds your neural architecture, attempting to understand something that by design you cannot truly grasp. This is the strange predicament of being human in a cosmos that may extend forever. We are finite minds touching the infinite, comprehending that it exists while remaining fundamentally incapable of comprehending what it is. The sections that follow will examine the scientific evidence for different types of physical infinity. We will explore whether space extends forever beyond every horizon. We will investigate whether time stretches infinitely in both directions, toward eternal past and eternal future. We will confront the infinities that appear in the equations of physics themselves. Quantities that may genuinely reach infinite values at singularities and cosmic extremes. But throughout this journey, remember the cognitive barrier we carry with us. Every concept ahead will bump against the walls of minds designed for counting gazelles on finite planes. Every infinity we discuss will exceed what your neurons can truly contain. We will learn about infinity without ever truly learning what infinity is. Infinity is not difficult because you are not trying hard enough. Infinity is not confusing because you lack intelligence or education. Infinity is difficult because you are human. And being human means having a brain that cannot contain the boundless, cannot visualize the endless, cannot truly process what forever means. All we can do is point toward infinity with our limited tools and acknowledge that something vast exists beyond the horizon of our comprehension. This is the first truth about infinity that cosmology reveals. The problem is not out there in the cosmos. The problem is in here, inside the neural architecture we inherited from ancestors who never needed to count past their fingers. We are apes trying to comprehend eternity. We are primates puzzling over the infinite. And we are beginning to realize that eternity may not be metaphor or poetry or philosophical speculation, but literal description of the universe we call home. The cosmos may actually extend forever. Time may actually stretch without end. Certain quantities may actually reach infinite values. And we are stuck trying to understand this with brains that cannot reliably distinguish between 1 billion and 1 trillion. That treats saving one life and saving 1 million lives with similar emotional weight. That visualize infinity as merely very large, rather than fundamentally different from every finite quantity. We cannot upgrade our neurons. We cannot install new cognitive hardware better suited for cosmic contemplation. We can only acknowledge our limitations, use our mathematical tools to probe beyond what we can intuit, and stand in appropriate wonder at a reality that exceeds everything our evolution prepared us to comprehend. The infinite exists. We cannot truly understand it, and we must proceed anyway, pointing our limited minds toward the unlimited, comprehending that there is something there while remaining incapable of comprehending what it is. This is the human condition in an infinite cosmos. This is what it means to be finite beings, awakening to the boundless reality we inhabit. Look up at the night sky and ask the simplest question a human being can ask about the cosmos. How far does it go? For most of human history, this question had no scientific answer and barely qualified as a meaningful inquiry. The stars seemed fixed against a celestial dome of unknown composition, perhaps infinitely distant, perhaps reachable if only we could climb high enough or build tall enough towers. Ancient astronomers mapped the positions of these lights without any understanding of what they actually were or how far away they hung in the darkness above. Modern astronomy has transformed this ancient mystery into precise measurements with disturbing implications that challenge everything our intuitions assume about the nature of existence. Space extends at least 46 billion light years in every direction from Earth. This observable volume contains approximately 2 trillion galaxies, each harboring hundreds of billions of stars, many hosting planetary systems where conditions might support life as we understand it. The scale already exceeds what human minds can genuinely comprehend. But here is what keeps cosmologists awake at night. What makes them stare at their equations with a mixture of wonder and unease? That vast observable volume, everything we can see with our most powerful telescopes, every galaxy we have ever photographed, every distant quasar whose light has traveled for billions of years to reach our instruments, may represent merely the visible portion of an actually infinite cosmic expanse. The observable universe might be to total reality what a single water droplet is to all the oceans of Earth, except infinitely smaller than even that comparison suggests. The shape of the universe determines whether space is finite or infinite. This statement might sound strange or even nonsensical on first encounter. How can space itself have a shape? Space seems like the empty stage on which objects exist rather than something with properties of its own. But one of the profound insights of modern physics is that space possesses geometric properties just as surely as surfaces and solids do. Geometry applies to the fabric of space itself, not merely to objects embedded within it. Consider how geometry works on different surfaces. A sphere has positive curvature, meaning parallel lines eventually converge no matter how they start. Lines of longitude on a globe appear parallel at the equator, but meet at the poles. A saddle shape has a negative curvature, where parallel lines diverge forever, spreading farther apart the longer they extend. A perfectly flat surface has zero curvature, where parallel lines remain parallel forever, regardless of how far you extend them. These different geometries produce different mathematical properties, different relationships between distances and angles, different rules governing motion and measurement. Einstein's general relativity, confirmed by over a century of experimental verification, predicts that the geometry of space depends on the total energy density of the universe. Matter and energy curve space-time. The more matter and energy packed into a region, the more curved space becomes in that region. On cosmic scales, the average density of all matter and energy throughout the universe determines the overall geometry of space itself. If the cosmic density exceeds a critical value, space curves positively and closes back on itself like the surface of a higher dimensional sphere. This creates a finite universe where traveling far enough in any direction eventually brings you back to your starting point, just as walking in a straight line on Earth's surface eventually returns you to where you began. Such a universe has no edge, no boundary, no wall where space ends, yet it contains finite volume, finite matter, finite extent. If cosmic density falls below the critical value, space curves negatively and extends infinitely in all directions with geometries stranger than flat surfaces can represent. Parallel lines diverge forever. Triangles have angles summing to less than 180 degrees. The mathematics becomes counterintuitive but remains perfectly consistent. If cosmic density equals the critical value exactly, space is flat in the geometric sense. Parallel lines remain parallel forever. Triangles have angles summing to exactly 180 degrees. Euclidean geometry, the geometry taught in high schools, applies perfectly at cosmic scales. And flat geometry is consistent with space extending infinitely in all directions without curvature, without closure, without any mechanism to make it finite. Scientists have measured cosmic geometry with extraordinary precision using the cosmic microwave background radiation that fills all of space. This ancient light left over from the Big Bang, emitted when the universe was only 380,000 years old, carries imprints revealing the curvature of space through which it has traveled for over 13 billion years. The patterns in this radiation, the specific sizes and distributions of hot and cold spots across the sky, depend sensitively on cosmic geometry. The Planck satellite, launched in 2009 and operational for several years, measured the cosmic microwave background with unprecedented accuracy. Scientists analyzed this data to determine cosmic curvature to within approximately 1% precision. The result shocked many physicists who had expected to find slight curvature indicating a finite cosmos. Space appears geometrically flat within every measurement we can make. The curvature, if any exists, is too small to detect with our best instruments. A flat universe is consistent with infinite spatial extent. Not proven infinite by this measurement alone, but entirely consistent with infinity. The observable universe we can detect, that sphere 93 billion light-years across, containing 2 trillion galaxies and more stars than grains of sand on Earth, represents a finite volume carved from what may be limitless space, extending forever beyond our cosmic horizon, in every direction simultaneously. This distinction between observable and total matters enormously for understanding our cosmic situation. The observable universe represents everything we can ever possibly see using any technology humans might develop. Light from beyond the observable horizon has not had time to reach us since the Big Bang occurred. Even if we waited another billion years or another trillion years, light from sufficiently distant regions would never arrive because cosmic expansion carries those regions away faster than light can travel toward us. But lack of observable evidence does not mean lack of existence. Space almost certainly extends beyond our observational limits. The cosmic microwave background radiation arrives from near the edge of the observable universe, proving that matter and energy exist out there at the boundaries of what we can see. There is no reason to suppose that space suddenly ends precisely where our ability to observe ends. The horizon is an artifact of light travel time, not a physical boundary in space. The question that haunts cosmology is whether space beyond our horizon extends finitely, eventually curving back or reaching some edge, or whether it extends infinitely without any terminus regardless of how far you travel. Current cosmological models strongly favor infinite extent. The standard lambda cold dark matter model, which successfully explains cosmic microwave background patterns, galaxy clustering measurements, supernova observations, and cosmic expansion rates, assumes a spatially infinite universe as its default configuration. Finite alternatives exist within the theoretical framework. Space could have exotic topology, wrapping back on itself through higher dimensional connections that our geometry cannot directly represent. Space could curve so slightly that the closure happens far beyond our observable horizon. These possibilities cannot be ruled out with current observations, but they require additional assumptions without observational support. The simplest interpretation of the data, the configuration requiring fewest extra hypotheses, is that space extends infinitely in all directions. Consider what infinite space actually means in concrete terms rather than abstract mathematics. Beyond the edge of observable space, beyond the furthest galaxy whose light can ever reach Earth, lies more space, containing more matter, more galaxies, more stars, more planets. Beyond that additional space lies still more space, still more galaxies, still more potential for existence. This pattern continues forever without termination. There is no wall where space ends. There is no boundary marking where existence stops. There is no ultimate edge beyond which lies something called nothing. The concept of an edge to space is actually incoherent when examined carefully. What would lie on the other side of such an edge? If anything exists there, then space continues into that region. And the edge was not truly an edge. If nothing exists there, then what separates the existing space from the non-existent region? The question quickly becomes nonsensical. Ancient philosophers wrestled with this paradox millennia before modern cosmology provided observational constraints. If space is finite, what lies beyond its edge? If space is infinite, how can an actually infinite thing exist? The pre-Socratic philosophers, Parmenides and Zeno, developed arguments about infinity that still provoke debate in philosophy departments today. The atomists, Leucippus and Democritus, embraced infinite void extending forever, as necessary for atoms to move and combine. Aristotle rejected actual infinity while accepting that processes could continue indefinitely. Modern physics offers no easy escape from these ancient paradoxes, despite centuries of additional insight. Einstein's general relativity permits curved geometries where space can be finite yet unbounded, avoiding the problem of edges. A spherical universe has no edge yet contains limited volume, just as Earth's surface has no edge yet has limited area. You can walk forever on Earth without reaching an edge, yet the total surface area remains finite and measurable. Curved cosmic geometry could work similarly in 3 dimensions. But observational evidence does not support sufficient curvature for this elegant solution to apply. Space appears flat to within measurement precision, and flat geometry permits infinite extent. The universe might still be slightly curved, with the curvature too small for our instruments to detect. But there is no positive evidence for such curvature. The data is consistent with perfect flatness, extending infinitely in all directions. The implications of infinite space become increasingly strange and disturbing upon careful examination. If space extends infinitely and matter distributes roughly uniformly throughout, a distribution supported by observations to the limits of our vision, then infinite numbers of galaxies exist beyond our cosmic horizon. Not merely many galaxies, not billions or trillions or any finite number however large. Infinite galaxies. The word infinite here carries its full mathematical weight, not as hyperbole but as literal description of quantity. The mathematics of probability in infinite spaces leads to conclusions that feel impossible, yet follow logically from established premises. Consider all possible arrangements of matter within a region of space. Within any finite volume, only a finite number of distinct arrangements exist because matter comes in discrete particles and energy comes in discrete quanta. There are many possible arrangements, incomprehensibly many, but still a finite number. If the universe is infinite and contains finite types of particle arrangements, then every possible arrangement must occur somewhere within that infinity. Not might occur as a speculative possibility, must occur as mathematical certainty. Given infinite space and finite possibilities, every configuration that does not violate physical law exists somewhere, and indeed exists an infinite number of times throughout the cosmos. This includes arrangements of matter identical to Earth and everything on it. Somewhere beyond your cosmic horizon, if space is truly infinite as evidence suggests, another planet exists with your exact atomic configuration. every atom positioned precisely as atoms are positioned in and around you right now. Another version of you is reading another version of these words in another version of this room, on another planet, orbiting another star in another galaxy, inconceivably far from the galaxy you call home. The distance to your nearest identical copy can be calculated mathematically, given certain assumptions about the uniformity and randomness of matter distribution. The calculation yields a number so staggeringly large that writing it out in standard notation would require more digits than there are atoms in the observable universe. The number exceeds human comprehension by factors that themselves exceed human comprehension. But in an infinite cosmos, even this enormous distance appears infinite times. There are infinite copies of you, each separated from the others by these incomprehensible distances, each living out a life identical to yours in every atomic detail. This conclusion disturbs even physicists who understand the mathematics perfectly and accept its logical validity. The idea of infinite, identical copies seems to violate common sense about uniqueness and identity. If there are infinite versions of you, which one is the real you? The question assumes uniqueness that infinite space does not provide. Each version is equally real, equally conscious, equally convinced of their own singular existence. Yet this disturbing conclusion follows directly from combining just two premises. Space is infinite. Physics is uniform throughout space. If both premises hold, and current evidence supports both, the existence of duplicates becomes mathematical certainty rather than philosophical speculation. The only ways to avoid this conclusion are to reject infinite space, or to propose that physics varies so dramatically across cosmic distances that Earth-like configurations become impossible beyond certain boundaries. Some scientists reject infinite space precisely because its implications seem absurd, too strange to accept regardless of mathematical derivation. They argue that the apparent fine tuning of cosmic geometry, which appears flat to extraordinary precision, might indicate that our measurements remain insufficiently precise to detect slight curvature that would close space into a finite volume. Future observations with better instruments might reveal the boundaries we intuitively expect must exist. Others embrace infinite space with all its strange consequences as the best current description of reality. They argue that human intuition about uniqueness and boundaries evolved for finite environments and should not constrain cosmic reality. The universe has no obligation to match human expectations developed on African savannas for tracking finite numbers of predators and food sources. If mathematics and observation point toward infinity, we should follow that evidence regardless of how uncomfortable the conclusions make us feel. Inflation theory adds another layer of complexity and strangeness to this picture. Cosmic inflation proposes that space expanded exponentially during the first fraction of a second after the Big Bang. The expansion occurred so rapidly that a region smaller than an atom grew to cosmic scales in a time interval shorter than light could travel across a single proton. This rapid expansion stretched tiny quantum fluctuations into the density variations that eventually became galaxies and cosmic structures. Inflation explains several puzzling features of the observable universe, including its remarkable uniformity and geometric flatness. Without inflation, different regions of the observable universe would never have been in causal contact, unable to exchange heat or information, yet they appear to have nearly identical temperatures. Inflation solves this puzzle by proposing that all observable regions were once connected within a tiny volume before inflation stretched them apart. but inflation may not have stopped everywhere simultaneously. Eternal inflation models developed by physicists including Alan Guth, Andrei Linde, and Alexander Vilenkin suggest that inflation continues forever in some regions while ending in others. Quantum fluctuations cause inflation to stop in certain patches of space, allowing normal cosmic evolution to proceed within those patches. These patches expand into observable universes like ours. But between the patches, inflationary expansion continues indefinitely, constantly spawning new patches where inflation ends and new cosmic domains emerge. Our observable universe in this framework represents one bubble where inflation happened to stop, allowing matter to cool and condense into galaxies and stars and planets, and eventually conscious observers who wonder about cosmic structure. But beyond our bubble, inflationary expansion continues even now, producing infinite additional bubbles, each representing its own observable universe within the larger inflationary structure. If eternal inflation accurately describes reality, then not only is space infinite, but our entire observable universe is just one island in an infinite sea of similar islands. Each bubble develops independently, potentially with different physical constants and laws determined by how quantum fields settled when inflation ended in that region. Some bubbles might have stronger gravity, others might have different fundamental particles. Some might be utterly inhospitable to any form of complexity or life as we conceive it. The multiverse that results from eternal inflation contains not just infinite copies of our cosmic neighborhood, but infinite variations as well. Every possible physics that eternal inflation could produce gets produced somewhere, infinite times, across an infinite landscape of cosmic bubbles separated by eternally inflating space that no signal can ever cross. Some physicists consider eternal inflation's implications too extravagant to accept as legitimate science. They argue that untestable predictions about regions we can never observe do not constitute scientific claims at all, regardless of their mathematical derivation. They seek inflationary models that produce finite outcomes or reject inflation entirely in favor of alternative early universe theories that avoid eternal expansion. But eternal inflation currently represents the default expectation from combining our best understanding of quantum field theory with cosmic observations. The physics that produced our observable universe, if we understand it correctly, seems to produce eternal inflation naturally without requiring special initial conditions or fine-tuning. Avoiding eternal inflation requires adjusting the theory in ways that seem arbitrary, designed specifically to eliminate uncomfortable conclusions rather than to improve predictive accuracy. The scale differences involved in these cosmological frameworks exceed human comprehension so completely that they render normal language nearly useless. If our observable universe, measuring 93 billion light-years, across represents a typical inflationary bubble, and if eternal inflation continues forever producing new bubbles, then the total spatial extent of reality exceeds our observable universe by factors that require new mathematical notation to express coherently. Consider a journey outward through these nested scales. Earth spans approximately 40,000 kilometers around its equator. The solar system, measuring from the Sun to the outer reaches of the Oort cloud where comets originate, spans perhaps 2 light-years. The Milky Way galaxy spans approximately 100,000 light-years, containing 400 billion stars. The observable universe spans 93 billion light-years, containing 2 trillion galaxies. Each step in this progression requires abandoning the previous scale as meaningful reference. By the time you comprehend the Milky Way's size, Earth has shrunk to irrelevance. By the time you grasp the observable universe, galaxies themselves blur into insignificance. And beyond the observable universe, if eternal inflation holds, space extends to distances that make the observable cosmos look like an atom floating within an infinite ocean, except even that comparison fails because atoms occupy finite proportion of oceans, while our observable universe occupies zero proportion of infinite extent. At each step of this scaling journey, your brain struggles to hold the previous scale while adding another level. By the time you reach eternal inflation cosmology, with its infinite bubbles spawning infinitely across an infinite inflating background, intuition has abandoned you entirely. You are manipulating symbols according to logical rules and following mathematical arguments that check out step by step, but genuine comprehension fled long ago. The pictures your mind generates bear no relationship to the reality the mathematics describes. This cognitive failure is not a sign of insufficient intelligence or inadequate education. It is a consequence of neural architecture fundamentally unsuited for processing these scales. Your visual cortex can handle images spanning perhaps 100 degrees of visual angle. Your spatial memory can navigate environments spanning perhaps tens of kilometers before losing accuracy. Your abstract reasoning can manipulate quantities up to perhaps millions before logarithmic compression becomes severe. Beyond these limits, you are performing mathematics without comprehension, reaching conclusions you can verify logically while having no genuine understanding of what those conclusions mean in terms of actual reality. Infinite space implies that no matter how far you travel, infinite distance remains ahead of you. A rocket accelerating forever, burning fuel endlessly, would never approach a boundary where space ended. It would pass galaxies, infinite galaxies, it passed stars, infinite stars, past planets, infinite planets. After any journey, regardless of duration or distance, infinite journey would remain. The concept of completing a trip through infinite space is incoherent. There is no destination that represents arrival, no point where you can say the traversal is done. Time becomes strange in infinite space as well. Light speed limits information transfer to approximately 300,000 kilometers per second. Nothing, no signal of any kind, can travel faster than this cosmic speed limit. In infinite space, this limitation means that most of the universe remains forever causally disconnected from any given location. Signals from sufficiently distant regions can never reach us because the distance is too vast, even for light traveling since the beginning of cosmic time. This causal isolation creates infinite numbers of independent cosmic regions, each evolving without any knowledge of the others. Entire civilizations could rise and fall in distant regions. Stars could form and explode. Black holes could grow to billions of solar masses and eventually evaporate through Hawking radiation. Complete cosmic histories could unfold, repeat, and diverge again, all without any possibility of those events ever influencing Earth, or being influenced by anything that happens here. We are not merely geographically isolated within an infinite cosmos. We are causally isolated, fundamentally disconnected from most of existence by the physics of light speed and cosmic distances. The infinite copies of you that mathematics predicts cannot communicate with you. They cannot send messages that will ever arrive. They cannot receive any signal you might transmit. They exist in perfect isolation, despite sharing the same infinite space, separated by distances that no physics we know permits crossing. Some philosophers find this isolation disturbing, a confirmation of cosmic loneliness more profound than mere interstellar distances suggest. Others find it strangely liberating. If most of existence is causally disconnected from Earth, then most of existence is also irrelevant to Earth in any practical sense. Those infinite copies of you living their lives across infinite cosmic distances might as well exist in separate universes for all the difference they can make to your existence. Their reality is complete unto itself. Your reality is complete unto itself. The connections are purely mathematical, never causal or communicative. But this perspective offers cold comfort when contemplating what infinite space means for cosmic significance and meaning. Every achievement of human civilization, every discovery, every work of art, every relationship, every thought you have ever had, every feeling you have ever experienced, all of it occurs within an infinitesimally small region of an infinite cosmos. Not metaphorically small or comparatively small, literally infinitesimally small in the mathematical sense. Any finite region divided by infinite extent equals exactly zero. This mathematical fact challenges assumptions about significance and meaning that most humans carry unexamined throughout their lives. If the universe is infinite, then Earth and everything on it represents 0% of cosmic reality. Not approximately zero, which might still represent something small but real. Exactly zero. The ratio of any finite quantity, however large, to infinity is mathematically identical to zero. This is not an approximation or simplification. It is a precise mathematical truth. Human intuition rebels violently against this conclusion. Surely we must matter somehow. Surely our existence has some cosmic significance that mathematics cannot capture. Surely the fact that we exist, that we think, that we love and create and wonder, counts for something in the ledger of cosmic importance. But mathematics offers no support for this intuition. In an infinite universe, finite creatures occupy exactly zero volume, contain exactly 0% of cosmic matter, and span exactly zero portion of cosmic extent. The arithmetic is merciless. Some philosophers find meaning precisely within this mathematical insignificance, rather than despite it. The fact that we exist at all, that consciousness somehow emerged from unconscious matter, that we can contemplate infinities we cannot comprehend, seems remarkable regardless of our cosmic percentages. Meaning might derive from the quality of existence rather than its quantity, from the internal relationships and experiences that characterize life rather than from external cosmic proportion. Others find the mathematical verdict genuinely crushing and seek finite cosmologies where significance might have mathematical grounding. If the universe is finite, then Earth represents some non-zero fraction of existence, however small. Some philosophers argue that meaning requires finitude, that infinite existence renders all achievements equally infinitesimal and therefore equally meaningless. Observational evidence continues accumulating but cannot definitively resolve whether space is finite or infinite. We can measure cosmic geometry with increasing precision as technology improves. We can constrain the minimum size of any finite universe to volumes vastly exceeding the observable cosmos, pushing hypothetical cosmic boundaries far beyond where our instruments can reach. But we cannot prove that space extends forever, because our observations remain fundamentally limited to the observable sphere carved out by light travel time since the Big Bang. What we can say with scientific confidence is that current evidence favors infinite extent. The observed geometric flatness of space, accurate to within 1% and perhaps much better, is precisely what infinite flat space would produce. The success of inflationary models, which naturally tend toward eternal inflation and infinite spatial extent, supports the infinite interpretation. The theoretical naturalness of infinite configurations, requiring no special boundary conditions or cosmic edges, points toward a universe without spatial boundaries. Scientists hold this conclusion tentatively, as they hold all conclusions, subject to revision if future observations suggest otherwise. A finite universe remains possible and would resolve some philosophical puzzles while creating others. But the default expectation among working cosmologists based on current evidence is that space extends infinitely in all directions and will never be found to end no matter how far our instruments can eventually probe. If this expectation proves correct, then you exist within a cosmos that genuinely has no walls. The observable universe, with all its 2 trillion galaxies and countless stars, represents a finite bubble of visibility within an infinite ocean of existence. Beyond your cosmic horizon lies not a boundary, but simply more existence, stretching forever in every direction. More galaxies, more stars, more planets, more possibilities, extending infinitely without termination. And somewhere out there in that infinite expanse, if the mathematics holds as it appears to hold, infinite versions of everything you have ever known exist repeated infinitely throughout endless space. Infinite Earths, infinite histories, infinite versions of you reading infinite versions of these words and wondering what it all means. The numbers are infinite. The distances are infinite. The implications stretch toward infinities of their own that compound the incomprehensibility. This is the universe that modern cosmology reveals when we ask the ancient question of how far space extends. Not the bounded cosmos of ancient intuition, where crystalline spheres contain the stars and celestial boundaries mark the edge of creation. Something far stranger, far larger, and far more disturbing to minds that evolve for finite environments. Space may actually extend forever without end or boundary or wall. And our brains, designed for counting predators on finite savannas, cannot truly contain what that cosmic endlessness means. Point backward through cosmic history and ask the most fundamental question about existence. How far does the past extend? Point forward through time yet to unfold, and ask the same question about the future. The arrow of time stretches in both directions from this present moment, and modern physics suggests something deeply unsettling about both endpoints. Time may extend infinitely in both directions, without beginning and without end. This possibility transforms the Big Bang from the origin of everything into merely an event within a larger eternal structure. It transforms the distant future from eventual cosmic conclusion into endless continuation without termination or rest. Infinite time disturbs human psychology even more profoundly than infinite space. We observe space from a distance, looking out at galaxies and cosmic structures that exist simultaneously with our observation. But we experience time directly, moment by moment, as the medium through which consciousness flows. The past feels genuinely gone, vanished into memory and history. The future feels genuinely open, not yet determined, awaiting our choices and cosmic chance. The suggestion that both past and future extend infinitely challenges not just our cosmological understanding, but our most basic experience of what it means to exist. The Big Bang occurred approximately 13.8 billion years ago. This statement appears in every astronomy textbook, every popular science documentary, every educational summary of cosmic history. Students learn it as established fact alongside the age of Earth and the distance to the moon. But what does this statement actually mean when examined carefully? The answer is far more subtle and strange than most people realize. The Big Bang marks the moment when our observable universe began expanding from an extremely hot, dense state. Every galaxy we can observe was once compressed into a region smaller than an atom. The expansion we see today, with galaxies rushing apart and space itself stretching, traces back to that initial explosive emergence. But this description carefully avoids a crucial question. The Big Bang marks when expansion began, but does it mark when time itself began? Does it represent the first moment of existence, the boundary before which nothing existed because there was no before? Standard cosmology describes the Big Bang as an initial singularity where density and temperature reach infinite values and the known laws of physics break down completely. Run the expansion backward, rewinding cosmic history like a film played in reverse. Galaxies crowd together, space compresses, temperature and density climb without apparent limit. At time zero, the mathematics predicts infinite density, infinite temperature, infinite curvature of space-time. The equations produce infinities rather than meaningful numbers. But physicists have learned through hard experience that singularities in equations typically indicate where theories fail rather than where reality becomes genuinely infinite. When equations produce infinities, the usual interpretation is that the mathematical framework being used has exceeded its domain of validity. Something different happens in reality, something the current theory cannot describe. The singularity marks ignorance rather than infinite physical quantities. General relativity, Einstein's theory of gravity that governs cosmic evolution, breaks down at the extreme conditions near the Big Bang. Quantum effects become important when matter compresses to such tiny scales, but we lack a complete theory of quantum gravity that could describe those conditions accurately. The true nature of the Big Bang, if a true nature exists, lies hidden behind quantum gravity effects we cannot yet calculate. This means that asking what happened before the Big Bang may not be like asking what lies north of the North Pole, a question with no answer because the question itself is malformed. It may instead be a legitimate question that our current physics simply cannot address. Something may have existed before the Big Bang, and that something may extend infinitely backward through time. Eternal inflation offers one framework for understanding what that pre-Big Bang existence might involve. In this theoretical picture, the Big Bang represents the moment when cosmic inflation ended in our particular region of space, not the beginning of existence itself. Inflationary expansion was already occurring before our Big Bang, had been occurring for an indefinite duration, and continues occurring in other regions even today. Our cosmic history with its 13.8 billion years represents one chapter in an eternally ongoing process that has no first chapter. The physics of eternal inflation arises naturally from quantum field theory applied to the early universe. Inflation occurs when a quantum field called the inflaton pervades space with energy that drives exponential expansion. This expansion continues until quantum fluctuations cause the inflaton field to decay into ordinary matter and radiation, ending inflation and triggering what we call the Big Bang. But quantum fluctuations are random. They do not occur everywhere at once. While inflation ends in some regions, it continues in others. The mathematics reveals something remarkable about this process. Inflationary expansion creates new space faster than quantum fluctuations can end inflation everywhere. For every region where inflation stops and a universe like ours emerges, vast amounts of new inflating space have been created where inflation continues. The process can never complete. New inflationary regions always form faster than old regions can transition to normal cosmic evolution. The net result is inflation that never completely stops anywhere throughout all of space and time. It has always been occurring somewhere, producing new cosmic regions continuously. It always will be occurring somewhere, spawning new universes forever into the future. And most disturbingly for our intuitions about beginnings, it has always been occurring. The inflationary process extends infinitely backward through time, as well as infinitely forward. This means asking when inflation began is like asking where the edge of infinite space lies. The question assumes a structure that may not exist. There was no first moment when inflation started because inflationary expansion extends infinitely backward through the temporal dimension. Our Big Bang occurred approximately 13.8 billion years ago within this framework, but that event represents a local transition, not a cosmic origin. Inflation itself has been occurring forever. Some physicists reject eternal inflation precisely because infinite past duration seems philosophically and logically problematic. How can an infinite number of events have already occurred before the present moment? This appears to involve completing an infinite sequence, which seems logically impossible. To reach the present from an infinitely distant past would require traversing infinite duration, which by definition cannot be completed. The present moment would never arrive because infinite time would need to pass first. This ancient paradox, debated by philosophers since antiquity, appears to demonstrate that infinite past is impossible. Zeno of Elea formulated the related paradoxes about infinite divisibility that troubled Greek mathematicians. The philosopher Immanuel Kant argued that both finite and infinite past lead to contradictions, suggesting the question transcends human reason entirely. Yet, eternal inflation's mathematics does not require completing infinity in the sense of counting through infinite events sequentially. It merely requires that no first moment exists, that every moment has preceding moments extending infinitely backward. This is different from traversing infinity. The present moment does not arrive after infinite duration has passed. Rather, the present moment simply exists at its location in an infinite temporal sequence, just as any point in infinite space simply exists at its location without having been reached by traversing infinite distance. The philosophical puzzles multiply when contemplating what infinite past implies for existence and causation. If infinite time preceded the present, why did the present arrive now rather than infinitely earlier? In an infinite past, any event that could occur should already have occurred. Any configuration of matter that physics permits should have been realized. Any thought that could be thought should have been thought. The present moment seems arbitrary. One moment among infinite others, with no special status or significance. More troublingly, in an infinite past, every event that could happen has already happened infinitely many times. If you exist now, then configurations of matter identical to you have existed before, infinitely often, throughout the infinite past. Your sense of experiencing this moment for the first time is an illusion, or at least configurations identical to you have experienced identical moments countless times before across eternal duration. These strange implications may reflect limitations of human time perception, rather than genuine paradoxes about temporal infinity. We experience time as flowing from past to future, as a river carrying us from earlier to later moments. This experience makes it natural to ask about first moments, about how sequences begin, about the origin point from which the flow started. But physics increasingly suggests this flowing time is an artifact of consciousness rather than a fundamental feature of reality. Einstein's relativity treats time as a dimension fundamentally similar to space. Just as every point in space simply exists at its coordinates without having been reached through traversal, every moment in time simply exists at its temporal coordinate. The equations do not distinguish past from future. They describe a four-dimensional block universe where all moments exist together, with the appearance of flow arising from how consciousness samples this static structure. If this block universe picture is correct, questions about first moments become as meaningless as questions about edges of infinite space. Infinite past does not require traversing infinite duration, any more than infinite space requires traveling infinite distance. Both simply exist as extended structures that consciousness encounters locally. The future presents similar conceptual puzzles, but with different emotional resonance. Looking forward rather than backward, will time continue forever or eventually reach some termination? Will the universe persist eternally, or does cosmic history have a final chapter where change ceases and existence ends? Modern cosmology predicts a future so incomprehensibly long that human timescales become meaningless units of measurement. The transformations ahead dwarf anything in cosmic history so far, by factors that require scientific notation to express. And the sequence of changes extends toward durations that may genuinely be infinite. In approximately 5 billion years, the Sun will exhaust the hydrogen fuel in its core that powers current nuclear fusion. The core will contract and heat up, eventually igniting hydrogen fusion in a shell around the core. This shell burning will cause the Sun's outer layers to expand enormously, transforming our star into a red giant with a diameter exceeding Earth's current orbit. Earth itself will be rendered uninhabitable long before this expansion completes, scorched by increasing solar luminosity as the Sun brightens over the coming billions of years. Human civilization, if it still exists in recognizable form, must migrate to other star systems or perish alongside our dying Sun. This may seem like an impossibly distant deadline, and it is on human timescales, but 5 billion years is less than half the current age of the universe. In cosmic terms, the death of our Sun represents a near-term local event, not a distant abstraction. But individual stellar deaths represent trivial events in the full, temporal extent of cosmic evolution. The Sun is one star among 400 billion in our galaxy, one galaxy among 2 trillion in the observable universe. Stars will continue forming and dying throughout the cosmos for timescales that dwarf solar system lifetimes. The raw material for new stars, hydrogen and helium gas floating in interstellar clouds, will gradually be consumed or locked away in stellar remnants. New star formation will slow over hundreds of billions of years, eventually ceasing entirely when no suitable gas remains. The last star will form and eventually exhaust its fuel approximately 100 trillion years in the future. 100 trillion years. Write out that number in full notation and contemplate what it represents. 100 million years. The current age of the universe, 13.8 billion years represents less than 1% of 1% of this stellar epoch duration. After the last star burns out, the universe enters what cosmologists call the degenerate era. Only stellar remnants remain, white dwarfs and neutron stars and black holes slowly cooling in the darkness. No new light sources exist, no stellar furnaces warm planetary surfaces. The cosmos becomes a vast graveyard of dead stars drifting through expanding emptiness. White dwarfs will cool slowly, incredibly slowly, their stored heat radiating away over timescales that exceed the current cosmic age by factors of millions. A white dwarf reaches the temperature of the cosmic microwave background, effectively becoming invisible after approximately 10 to the 15th power years. 1,000,000 billion years. Written out in full, that number fills paragraphs. And by cosmic standards, even this represents a relatively early phase of future evolution. Black holes will persist far longer than any other stellar remnant. They do not cool or radiate in conventional ways. Instead, they slowly evaporate through Hawking radiation, a quantum mechanical process that causes black holes to emit particles and gradually lose mass over incomprehensible durations. A stellar mass black hole, perhaps 10 times the Sun's mass, requires approximately 10 to the 67th power years to evaporate completely. Write out 67 zeros after the 1 and try to comprehend what duration that represents. Your attempt will fail utterly. The largest supermassive black holes, containing billions of solar masses and sitting at the centers of galaxies, require even longer, approximately 10 to the 100 power years. This number, called a Google years, exceeds the number of atoms in the observable universe. These cosmic monsters will persist as the last concentrated structures in a universe, otherwise dissolved into thin radiation and scattered particles, slowly shrinking over durations that make the previous eras look instantaneous. After the last black hole evaporates, the universe enters a state of maximum entropy where nothing interesting can happen in any conventional sense. Temperature everywhere approaches absolute zero. Particle densities become so low that interactions between remaining particles become vanishingly rare. The cosmos consists of extremely dilute radiation and scattered particles drifting through ever-expanding space, approaching but never quite reaching perfect thermal equilibrium. This is the heat death of the universe, a concept first articulated by physicists in the 19th century and refined by modern cosmology. The name is misleading. Heat death is not a dramatic ending, not an explosion or collapse or sudden termination. It is a gradual fade into permanent equilibrium, where the thermodynamic gradients that permit interesting processes no longer exist. Without temperature differences, no engines can operate. Without energy flows, no computation can occur. Without structure, no complexity can persist. The key question that haunts consideration of heat death is whether it represents the end of time itself or merely an eternally boring phase within ongoing time that continues forever. Physics does not provide clear guidance on this question. Time could continue indefinitely through the heat death era, moment following moment forever, with no events occurring to mark temporal passage. Or time might be defined by events, by change, by difference between moments. If nothing ever changes, does time still pass? Different physical frameworks suggest different answers. In relativity, time is a dimension that exists regardless of what happens within it. Empty space-time is still space-time, with temporal extension whether or not events occur. In thermodynamic approaches, time's arrow depends on entropy increase. Once maximum entropy is reached, the arrow of time has no direction to point. In quantum mechanics, time appears in the equations as a parameter that continues regardless of system states. Some theoretical frameworks suggest the universe could undergo phase transitions after heat death, creating new epochs of activity from apparent cosmic exhaustion. Quantum fluctuations never truly stop. Even in maximum entropy equilibrium, random fluctuations occasionally create local decreases in entropy, temporary structures emerging from uniformity before dissolving back. Usually these fluctuations are tiny, just a few particles momentarily arranged in unusual configurations. But given infinite time, even extraordinarily improbable fluctuations eventually occur. A fluctuation large enough to create a new Big Bang, a new inflationary region, a new cosmic domain where complexity can evolve, would be fantastically unlikely at any given moment. The probability is so low that writing it requires exponential notation, with exponents themselves requiring exponential notation. Yet, probability multiplied by infinite time yields certainty for any event that is possible, regardless of how improbable. If such fluctuations can occur, they would eventually occur given infinite duration. The dead universe might be periodically punctuated by new cosmic births, fresh islands of activity emerging from equilibrium through random chance. The sequence of universes might extend forever. Heat death, followed by fluctuation, followed by new cosmos, followed by new heat death, repeating infinitely throughout eternal time. This possibility connects to one of the strangest and most disturbing arguments in modern physics, a problem that has caused genuine distress among cosmologists who contemplate its implications carefully. The Boltzmann brain problem challenges our understanding of observation, probability, and what it means to be a real, conscious entity in a universe of infinite duration. In a universe that continues forever, random quantum fluctuations would occasionally create arrangements of matter, mimicking any configuration possible within physics. Given infinite time, fluctuations would eventually create not just particles in unusual arrangements, but complex structures, even structures that briefly embody consciousness. A brain complete with neurons and electrochemical activity could fluctuate into existence from random thermal motion. Such a brain would have apparent memories of experiences it never actually had, beliefs about a world it never inhabited, a sense of continuous personal history that is entirely false. These hypothetical entities are called Boltzmann brains after the physicist Ludwig Boltzmann, who first considered related problems about thermodynamic fluctuations. A Boltzmann brain would flicker into existence, experience perhaps a single moment of confused consciousness before the same random processes that created it destroyed it and dissolved back into thermal equilibrium. It would never know its memories were fabrications, its experiences unreal, its existence a momentary accident rather than the product of cosmic evolution. The problem arises from comparing numbers. How many real observers exist in a universe with infinite future duration? A finite number. However many civilizations evolve throughout cosmic history before heat death arrives, the count is finite. Extremely large, perhaps, but finite. How many Boltzmann brains fluctuate into existence given infinite time? An infinite number. Any non-zero probability multiplied by infinite duration produces infinite expected occurrences. If real observers are finite and fluctuation observers are infinite, then the vast majority of conscious experiences in the universe are Boltzmann brain experiences. Almost all moments of consciousness throughout cosmic eternity belong to confused, false entities rather than beings with genuine histories. The probability that any given experience is real rather than fluctuated becomes essentially zero. This creates a disturbing prediction that seems to undermine empirical science itself. If you're probably a Boltzmann brain rather than a real observer, then your memories of performing experiments, me collecting data, and reasoning about cosmology are probably fabrications. The evidence you think supports your theories is probably false evidence implanted by random fluctuation. The reasoning that led you to conclude Boltzmann brains are likely is itself probably unreliable, because your brain is probably a Boltzmann brain with false reasoning patterns. Some physicists use this apparent absurdity to constrain cosmological theories. Any theory predicting infinite future duration faces the Boltzmann brain problem, and might be rejected on grounds that it produces self-undermining conclusions. If a cosmological model predicts that most observers are Boltzmann brains, perhaps that prediction indicates the model is wrong. This reasoning has been applied to reject certain versions of eternal inflation and certain assumptions about the future of our universe. Others argue that Boltzmann brains present no genuine problem because we have no way of knowing whether we are real observers or fluctuation observers. The question may be meaningless or unresolvable within any framework we could construct. If real observers and Boltzmann brains have identical experiences at the moment of experience, perhaps no basis exists for distinguishing them or for claiming one type is more common than another. The arrow of time introduces additional complications to understanding infinite temporal extent. In everyday experience, time clearly flows from past to future with unmistakable directionality. We remember yesterday, but not tomorrow. We can influence future events through present choices, but cannot change past events regardless of present regret. Causes precede effects. Eggs break, but do not unbreak. Coffee cools, but does not spontaneously heat. This temporal asymmetry seems absolutely fundamental to the structure of existence itself. Yet the fundamental laws of physics are almost perfectly time-symmetric. Run any microscopic physical process backward, and it remains entirely consistent with the equations governing physical reality. A video showing molecules bouncing around in a box looks equally valid whether played forward or backward. Newton's laws, Maxwell's equations, even quantum mechanics at the fundamental level do not distinguish past from future. Time reversal symmetry holds at the deepest level of physical description. The arrow of time that we experience so unmistakably emerges not from fundamental physics, but from special initial conditions at the Big Bang. The early universe had extremely low entropy, an extremely unlikely configuration among possible arrangements of matter and energy. This low entropy past allows entropy to increase toward the future, creating the thermodynamic arrow that governs macroscopic processes. Eggs break because breaking increases entropy. Coffee cools because heat flow increases entropy. Memory records the past because recording increases entropy. But if the past extends infinitely rather than beginning at a low entropy Big Bang, where did these special initial conditions come from? Why did the early universe have low entropy at all? What set the thermodynamic arrow pointing consistently from past toward future throughout our cosmic region? In an eternally inflating multiverse, different cosmic regions might originate with different initial conditions. Some might have low entropy pasts, allowing arrows of time like ours. Others might have different entropy configurations, producing arrows pointing in what we would consider reverse, with their inhabitants experiencing effect before cause, remembering what we would call future, and predicting what we would call past. Still, others might lack thermodynamic gradients sufficient for any arrow at all, with entropy fluctuating randomly rather than consistently increasing. These possibilities challenge the deepest human intuitions about temporal experience. We perceive time as absolutely fundamental, as the irreversible medium through which existence flows, but physics treats time as a dimension, potentially infinite like space, potentially reversible like space, potentially without privileged direction any more than space has a privileged direction. Consider what infinite future time means for individual existence and mortality. If you knew with absolute certainty that time continues forever, that the future extends infinitely without ever reaching conclusion or termination, how would that knowledge affect your experience of the present moment? Many people initially find the prospect of infinite future time comforting. It seems to guarantee that existence persists, that the cosmic story never ends, that something always comes next. But deeper reflection often reveals that infinite future carries terrors of its own, quite distinct from the terrors of finitude. Every possible experience would eventually occur within infinite time. Every thought would be thought. Every emotion would be felt. Every variation and permutation of existence would be explored exhaustively. And then what? The sequence continues with no possibility of ending, no final rest, no completion that provides closure. Some philosophers have argued that meaning requires finitude, that infinite existence would become meaningless precisely because nothing could ever conclude. In finite existence, choices matter because alternatives are permanently foregone. Achievements matter because time to achieve is limited. Relationships matter because they end. Remove all limits and perhaps nothing matters because everything will happen eventually regardless of present choices. Whether infinite future would provide eternal significance or eternal meaninglessness may be a question that finite beings like humans simply cannot answer. Our intuitions about meaning, purpose, and significance develop for finite lifespans in finite environments. Asking whether infinite existence would be meaningful is like asking whether four-dimensional geometry would be comfortable. The question assumes our current framework applies at scales and conditions it was never designed to address. What cosmology can tell us with reasonable confidence is that time extends far longer than any human timescale in both directions. The past before human emergence contains 13.8 billion years of cosmic evolution, plus whatever preceded our Big Bang in eternally inflating frameworks. The future after eventual human extinction contains trillions of years of stellar evolution, Google years of black hole dominance, and potentially infinite duration beyond. If time is truly infinite in both directions, then human existence represents exactly 0% of temporal duration. The same mathematics that renders us spatially infinitesimal in infinite space renders us temporally infinitesimal in infinite time. Not approximately zero, which might still feel like something. Exactly zero. The ratio of any finite duration to infinite time is mathematically identical to zero, regardless of how long that finite duration extends. We naturally assume our era matters, that the present moment occupies some special position in cosmic history simply because we exist within it. We imagine ourselves at the culmination of cosmic evolution, at the frontier of complexity and consciousness, at a temporal location of unique significance. But infinite time suggests that every moment is equally surrounded by infinite past and infinite future. No moment is special, no era matters more than any other. No temporal location has privileged status compared to the infinite other locations extending in both directions. The present is distinguished only by our presence within it, and our presence represents infinitesimal duration within potentially infinite time. We are not at the culmination of cosmic history. We are not at any special point at all. We simply exist at our temporal coordinates, one moment among infinite moments, experiencing what exists here before dissolving back into the temporal sequence that continues forever, with or without us. This temporal insignificance mirrors spatial insignificance in its challenge to human assumptions about cosmic importance. Just as infinite space suggests we occupy zero volume of existence, infinite time suggests we occupy zero duration of existence. Just as infinite space contains infinite versions of Earth across endless spatial extent, infinite time may contain infinite versions of human history across endless temporal extent. Our sense of uniqueness, of existing at a special moment in cosmic history, dissolves into mathematical triviality when confronted with genuine temporal infinity. The next section examines infinities that appear not merely in the extent of space and time, but within the very equations that physicists use to describe physical reality. Space and time may extend forever as continuous backgrounds for existence. But even more disturbing are the infinities that physics predicts at specific locations and specific moments, singularities where physical quantities themselves become infinite rather than merely extending infinitely. These mathematical infinities appearing in our best theories terrify physicists because they signal the breakdown of understanding at precisely the points where understanding matters most. Something infinite lurks inside every black hole in the universe. At the center of these gravitational monsters, where matter has collapsed beyond any possibility of escape. General relativity makes a prediction that has haunted physicists for over a century. Matter collapses to a point of zero volume and infinite density. The curvature of space-time, the mathematical description of gravity's warping effect on the fabric of reality, becomes infinite. The equations that describe how gravity operates throughout the cosmos, equations that have passed every experimental test with extraordinary precision, produce nonsensical results at these extreme locations. Division by zero yields infinities that cannot be physically interpreted or experimentally verified. This mathematical catastrophe is called a singularity, and it represents where our understanding of physics breaks down completely. Not partially, not approximately, completely. The theories that work everywhere else in the universe, that accurately predict the motion of planets and the bending of starlight and the behavior of GPS satellites, simply stop functioning when applied to these extreme conditions. They produce infinity as their answer, which is no answer at all. Singularities are not rare curiosities hiding in exotic corners of theoretical physics. They are ubiquitous predictions of general relativity appearing whenever gravity becomes sufficiently strong. Every black hole in the universe contains one at its center. Stellar mass black holes formed from collapsed massive stars harbor singularities. Supermassive black holes containing billions of solar masses at the centers of galaxies contain singularities. The Big Bang itself, the origin event of our observable cosmic history, represents a singularity where the entire observable universe was compressed to infinite density in zero volume. Physicists hate these infinities appearing in their theories. They do not hate them for philosophical reasons or aesthetic preferences about how nature should behave. They hate them professionally, practically, because infinite predictions are scientifically useless. Science operates through prediction and verification. A theory makes specific numerical predictions that experiments can test. When predictions match measurements, confidence in the theory increases. When predictions fail, the theory requires revision or replacement. An equation that predicts a measurement of infinity provides no guidance whatsoever about what experiments will actually find. What instrument could measure infinite density? What observation could confirm infinite curvature? The number infinity cannot be compared to any finite measurement because infinity exceeds every finite quantity by definition. Infinite predictions are untestable predictions, and untestable predictions lie outside the domain of empirical science entirely. When physicists encounter infinities in their calculations, the standard interpretation is that the theory being used has exceeded its domain of validity. Every physical theory has limits, conditions beyond which its approximations and assumptions break down. Newtonian mechanics works beautifully for everyday objects, but fails at speeds approaching light. Classical electromagnetism describes macroscopic phenomena perfectly, but breaks down at atomic scales. The appearance of infinity typically signals that the mathematical framework being applied has reached its boundary, that something different happens in reality which the current theory cannot describe. Consider what general relativity predicts as you fall into a black hole. From your perspective as the infalling observer, you cross the event horizon, the boundary of no return, without noticing anything particularly special. Space and time continue in their normal relationship. You see light. You experience duration. The laws of physics appear unchanged in your immediate vicinity, but you are now falling inexorably toward the center, toward the singularity that awaits at the end of your plunge. As you descend, the curvature of space-time increases continuously. The tidal forces stretching your body grow stronger moment by moment. According to general relativity, this curvature continues increasing without limit as you approach the central singularity. At the singularity itself, curvature becomes mathematically infinite. The equations produce a result that has no physical meaning. What would you actually experience at that moment? What happens to matter when it reaches infinite density? What does infinite curvature feel like? The equations cannot say because they have stopped making sense. The symbols on the page produce results that cannot be interpreted as physical quantities. The prediction of infinity is really a prediction of theoretical failure. General relativity is telling us, in the only language it knows, that it cannot describe what happens at the center of black holes. Most physicists working on these problems believe that quantum mechanics intervenes before genuine infinities are reached. General relativity is a classical theory, meaning it does not incorporate the quantum effects that govern behavior at extremely small scales. When space-time curvature becomes sufficiently extreme, when matter compresses toward dimensions comparable to the Planck length, quantum effects must become important. A complete theory of quantum gravity, unifying Einstein's geometric description of gravity with the probabilistic framework of quantum mechanics, would presumably replace the infinite singularity with some finite structure that our current incomplete theories cannot describe. String theory, one leading candidate for quantum gravity, suggests that fundamental particles are not point-like objects, but tiny vibrating strings with finite extent. These strings cannot be compressed below a certain minimum size determined by the string tension and fundamental constants. If matter is ultimately composed of strings rather than points, singularities of zero volume and infinite density become impossible. Something else happens at extreme compression. Something finite and presumably describable once string theory is better understood. Loop quantum gravity, another approach to quantum gravity, suggests that space-time itself becomes discrete at the smallest scales rather than remaining a smooth continuum. Space comes in minimum chunks, tiny volumes that cannot be subdivided further. Time comes in minimum intervals, brief durations that represent the shortest possible temporal division. If space-time is fundamentally granular rather than continuous, infinite curvature becomes impossible because curvature cannot exceed what these minimum space-time units permit. But these theories remain incomplete, their mathematical structures not yet fully developed. Their predictions for black hole interiors and Big Bang conditions not yet calculable with confidence. We strongly suspect that quantum gravity resolves singularities, replacing infinite predictions with finite ones. But we cannot yet demonstrate this resolution through rigorous mathematical derivation from first principles. The infinities in general relativity remain unresolved in any complete sense. The Big Bang singularity presents the same puzzle at the origin of cosmic time, rather than at the center of collapsed stars. Running the expansion of the universe backward through cosmic history leads to a moment of infinite density and temperature. All matter and energy in the observable universe compressed into zero volume. All of cosmic history emerging from a mathematical point of infinite physical quantities. But this infinity likely indicates where general relativity fails rather than describing actual physical conditions that existed. Quantum effects must have been important when the entire universe compressed to scales where quantum mechanics governs behavior. Something happened at the Big Bang that our current physics cannot fully describe. The singularity represents a wall beyond which our theories cannot see, a boundary of knowledge rather than a genuine infinite quantity in physical reality. Whether that something involved true infinity or merely conditions so extreme that current theories cannot address them remains genuinely unknown. We cannot observe the Big Bang directly. We cannot recreate its conditions in any laboratory humans could build. We can only reason backward from present observations and forward from theoretical frameworks, hoping these two approaches will eventually meet in understanding that currently eludes us. The cosmological constant presents a different kind of infinity problem that has tortured theoretical physicists for decades. Quantum field theory, the mathematical framework describing how particles and forces behave at fundamental scales, predicts that empty space should contain energy from virtual particle fluctuations. The quantum vacuum seethes with particles constantly appearing and disappearing, borrowing energy from the uncertainty principle for brief moments before annihilating back into emptiness. These fluctuations contribute energy to the vacuum itself. Calculations of this vacuum energy produce infinite results. The contributions from virtual particles of arbitrarily high energy sum to infinity when integrated over all possible energies. This infinity must be handled through a mathematical procedure called renormalization, where infinite quantities are carefully manipulated to cancel against each other, leaving finite predictions that can be compared with experiments. Renormalization works extraordinarily well for most purposes. The predictions of quantum electrodynamics, the theory describing how electrons interact with photons, match experimental measurements to better than 10 decimal places of precision. No scientific theory in history has achieved such accuracy. The procedure for handling infinities, whatever philosophical discomfort it causes, produces results of unprecedented precision. But when this renormalized vacuum energy is used to calculate the cosmological constant, the energy density of empty space that affects cosmic expansion, the result is wrong by a factor of approximately 10 to the 120th power. Not wrong by 10% or a factor of 2 or even a factor of a million. Wrong by a number that requires 120 zeros to write out. This represents the largest discrepancy between theoretical prediction and observational measurement in the entire history of physics. Something about how quantum field theory handles infinities fails spectacularly when applied to gravitational phenomena at cosmic scales. The mathematical techniques that tame infinities beautifully in particle physics produce nonsense when extended to cosmology. Some deep understanding about the nature of infinity in physical law remains missing from our theoretical framework. The cosmological constant problem stands as one of the greatest unsolved mysteries in fundamental physics, a glaring indication that our handling of infinities contains errors we have not yet identified. Infinities appear throughout the standard model of particle physics, the mathematical framework describing all known fundamental particles and forces except gravity. When physicists calculate how electrons interact with photons using the straightforward approach suggested by the theory's structure, the calculations yield infinite results. The probability for certain processes comes out infinite. The corrections to particle masses come out infinite. The whole mathematical apparatus seems to produce nonsense when applied naively. Renormalization again provides rescue by absorbing these infinities into redefinitions of particle masses and charges. The bare parameters appearing in the original equations are themselves infinite. But these infinities precisely cancel the infinities from quantum corrections, leaving finite observable quantities that experiments can measure. The procedure works mechanically, step by step, producing predictions that match observations with extraordinary accuracy. But renormalization makes many physicists deeply uncomfortable precisely because it works so well. Why should a procedure for sweeping infinities under mathematical carpets produce the most accurate predictions in scientific history? The infinities appear in the calculations. They are real mathematical quantities emerging from the theory's structure. Then they are manipulated, combined, and cancelled through techniques that sometimes feel more like accounting tricks than fundamental physics. Either the infinities are telling us something important that we are ignoring, some deep truth about the structure of reality that manifests as these divergent quantities, or the mathematical structure of physics has features we do not fully understand that make renormalization natural rather than mysterious. Neither option is comfortable. Both suggest that our understanding of how mathematics relates to physical reality remains incomplete in fundamental ways. Some physicists argue that infinities in physics are signals pointing toward new physics beyond current theories. Just as the ultraviolet catastrophe in classical physics, where calculations of blackbody radiation produced infinite energy at high frequencies, pointed toward quantum mechanics and its resolution through Planck's quantization hypothesis, modern infinities might be pointing toward theories we have not yet discovered. The singularities in black holes might be resolved by string theory or loop quantum gravity once these frameworks are fully developed. The cosmological constant problem might be solved by a new understanding of how quantum fields couple to gravity at fundamental scales. The hierarchy problem, asking why the Higgs boson mass is so much smaller than quantum corrections suggest, might be resolved by supersymmetry or extra dimensions, or some entirely new theoretical framework. The persistent appearance of infinity throughout physics might be nature's way of indicating where our knowledge breaks down and where new understanding awaits. Each infinity marks a frontier, a boundary beyond which current theories cannot venture. Crossing these frontiers requires new ideas, new mathematics, new ways of thinking about the relationship between abstract equations and physical reality. Other physicists argue that some physical quantities might actually be infinite in the external world, rather than merely appearing infinite due to theoretical limitations. The spatial extent of the universe might genuinely be infinite rather than merely very large. The temporal duration of existence might genuinely extend infinitely, rather than merely to durations beyond current observation. The density at singularities might genuinely reach infinite values through physics we cannot currently describe, rather than being resolved into finite quantities by quantum effects. The reluctance to accept physical infinities might reflect cognitive limitations developed for finite environments rather than scientifically justified skepticism. Human brains evolved to process finite quantities because infinite quantities never appeared in ancestral environments. The instinctive feeling that infinities cannot really exist might be an artifact of evolution rather than insight into cosmic reality. The distinction between mathematical infinity and physical infinity lies at the heart of these debates and determines how physicists approach the infinities appearing in their equations. Mathematics routinely handles infinite quantities through rigorous techniques developed over centuries since Cantor's pioneering work. Infinite sets, infinite series, infinite dimensional spaces all have well-defined mathematical properties that can be manipulated according to precise rules. The mathematical concept of infinity is internally consistent and enormously useful for calculations throughout physics and mathematics. Physical infinity is far more problematic because it implies actual existence of boundless quantities in the external world rather than merely useful abstractions for calculation. Can infinite density actually exist as a physical state of matter? This question is not asking whether infinite density is mathematically consistent, which it clearly is within appropriate mathematical frameworks. It is asking whether the physical universe contains regions where density genuinely has no upper bound, where matter compresses beyond any finite description into states that no number, however large, can characterize. Some physicists believe the answer must be no, that physical quantities are always finite, even if sometimes extraordinarily large. Physics describes the relationship between measurable quantities. Measurements always yield finite results. Perhaps quantities that cannot in principle yield finite measurements do not qualify as physical quantities at all, but rather as mathematical artifacts or signals of theoretical breakdown. Others remain agnostic about whether physical infinities can exist. noting that human intuitions about what is physically possible have repeatedly proven wrong as science advanced. Atoms seemed indivisible until we split them. The speed of light seemed like an ordinary velocity until relativity revealed it as a cosmic speed limit. Time seemed absolute until Einstein showed it varies with motion and gravity. Perhaps the impossibility of physical infinity will prove to be another intuition that nature violates. Consider carefully what infinite density at the center of a black hole would actually mean if it genuinely exists rather than being resolved by quantum effects. The atoms, electrons, and quarks that comprised a collapsing star would be compressed into zero volume while retaining their identity as physical entities. Their quantum mechanical wave functions, the mathematical descriptions governing their behavior everywhere else in physics, would be crushed to mathematical points. The probabilistic descriptions that work throughout quantum mechanics would produce infinities that cannot be interpreted as probabilities. Most physicists expect that quantum effects prevent such literal compression to zero volume. The uncertainty principle itself seems to resist infinite compression. Localizing a particle to an infinitely small region requires infinite uncertainty in its momentum, which implies infinite energy. Perhaps this relationship places fundamental limits on how small any region containing matter can become. String theory suggests fundamental particles are extended objects with finite size that cannot be compressed below certain dimensions determined by fundamental constants. Loop quantum gravity suggests space-time itself becomes discrete at the Planck scale, with minimum volumes that cannot be subdivided further. Both approaches replace point-like singularities with finite structures, though neither has been developed completely enough to describe what those structures are like in detail. But these theories remain incomplete, their mathematical structures still under development, their predictions for extreme conditions still uncertain. We expect quantum gravity to resolve singularities, but we cannot yet demonstrate this resolution definitively. The question of whether infinite density can physically exist remains genuinely open. The information paradox adds another layer of conceptual difficulty to black hole physics and the infinities it contains. When matter falls into a black hole, the information describing that matter, the quantum states specifying its complete physical description, appears to be lost behind the event horizon, where it cannot be retrieved. The black hole itself, described by general relativity, has no hair, meaning it is characterized completely by just three numbers: mass, charge, and angular momentum. All the detailed information about what fell in seems erased. Eventually, the black hole evaporates through Hawking radiation, a quantum mechanical process where particles emerge from near the event horizon and carry energy away. This evaporation continues over incomprehensible timescales until the black hole completely disappears. The radiation left behind appears completely thermal, carrying no information about what originally formed the black hole. The detailed quantum states of the infalling matter seem permanently lost. This appears to violate quantum mechanics, which requires that information be conserved. Quantum evolution is unitary, meaning the present state uniquely determines both past and future states. Information cannot be created or destroyed, only transformed. Yet black holes seem to destroy information by converting detailed quantum states into thermal radiation with no memory of its origins. Recent theoretical developments suggest that information might be preserved through subtle correlations in the Hawking radiation, that become apparent only when the complete radiation is analyzed, or through holographic mechanisms where information is stored at the event horizon in ways not captured by naive calculations. But these solutions remain controversial, mathematically incomplete, and difficult to reconcile with. The infinite singularity that general relativity predicts at the black hole center. The tension between general relativity, quantum mechanics, and information theory at black hole singularities represents one of the deepest unsolved problems in physics. 3 of our most successful theoretical frameworks appear to contradict each other at precisely the locations where infinity emerges from the mathematics. Resolving this tension will likely require understanding what really happens where our current theories predict infinity. Temperature provides another arena where infinity appears in physical predictions with disturbing implications. As matter approaches a black hole singularity, tidal forces heat it to extraordinary temperatures. The gravitational gradient stretches and compresses matter, converting gravitational potential energy into thermal energy at prodigious rates. Near the singularity itself, where tidal forces become infinite according to general relativity, temperature, predictions diverge to infinity as well. The Hagedorn temperature in string theory represents a maximum possible temperature, where string excitations become arbitrarily complex. Above this temperature, which approaches the Planck temperature around 10 to the 32nd power Kelvin, conventional descriptions of matter break down entirely. Temperature as normally conceived may not exist beyond this limit. Something qualitatively different governs physics at such extreme conditions. The early universe passed through conditions approaching Hagedorn temperatures during the Big Bang. What physics governed matter at such extremes remains poorly understood. The infinities appearing in temperature calculations at singularities represent boundaries of current theoretical understanding rather than definitive predictions of physical conditions. Something happens at extreme temperatures that our theories cannot describe, just as something happens at extreme densities and curvatures. Energy presents similar puzzles throughout fundamental physics. Quantum field theory predicts that empty space contains infinite energy from vacuum fluctuations. Virtual particles of arbitrarily high energy contribute to the vacuum, and the sum over all possible energies diverges to infinity. This energy can be renormalized away for most calculations, hidden through mathematical manipulations that leave finite answers for observable quantities. But its presence haunts every attempt to understand how quantum fields interact with gravity. If vacuum energy is physically real, it should gravitationally affect cosmic expansion. Energy gravitates according to general relativity. Infinite vacuum energy would produce infinite gravitational effects, which we obviously do not observe. Yet if vacuum energy is merely mathematical artifact with no physical reality, why does renormalization, which treats these infinities as real quantities to be cancelled, work so extraordinarily well for calculating observable phenomena? The hierarchy problem highlights another troubling aspect of infinities in fundamental physics. The Higgs boson, discovered at the Large Hadron Collider in 2012, has a measured mass of approximately 125 billion electron volts. But quantum corrections to this mass from virtual particles of high energy suggest it should be enormously larger, close to the Planck mass where quantum gravity effects become important. These corrections come from virtual particles of arbitrarily high energy and produce infinite results that must be carefully cancelled to yield the observed Higgs mass. This cancellation requires extraordinary fine-tuning, with different contributions precisely balancing to many decimal places. Such precise cancellation seems improbable unless some underlying principle enforces it. Some deep structure in physics that makes the balance natural rather than coincidental. Supersymmetry was proposed partly to resolve this. Hierarchy problem by providing natural cancellations between contributions from different particle types. Every known particle would have a supersymmetric partner with different spin properties, and contributions from partners would naturally cancel without fine-tuning. But experiments at the Large Hadron Collider have not found supersymmetric particles where theoretical predictions suggested they should appear. Either supersymmetry exists at energies higher than current accelerators can reach, or some other mechanism controls the infinities in Higgs mass calculations, or our understanding of these infinities is fundamentally mistaken. What does it mean to exist in a universe where physical infinities might be genuinely real rather than merely signals of theoretical inadequacy? If space extends infinitely, we occupy exactly 0% of spatial existence. Any finite volume divided by infinite extent equals 0. If time extends infinitely in both directions, we occupy exactly 0% of temporal duration. Any finite lifespan divided by infinite time equals 0. If density genuinely reaches infinity at singularities, then somewhere in the universe exists matter compressed beyond any finite description, existing in states that no number can characterize. These possibilities challenge assumptions about the nature of reality that humans carry almost universally without examination. We naturally think of quantities as bounded, as having maximum and minimum values. Nothing weighs more than everything. Nothing is smaller than nothing. Quantities have floors and ceilings that constrain them within finite ranges. The possibility that the universe contains genuine infinities, quantities that exceed every bound and transcend every limit, requires abandoning these intuitions. Perhaps most disturbing is the possibility that we simply cannot know whether physical infinities exist. Our observations are limited to the observable universe, a finite sphere beyond which light has not had time to reach us. Our theories break down precisely where infinities appear, unable to describe what happens at singularities or beyond cosmic horizons. The question of whether infinity is physically real or merely mathematical convenience may be permanently beyond human determination. Some philosophers argue that this fundamental uncertainty is itself significant for understanding the human relationship to cosmic reality. If we cannot determine whether infinity exists in physical reality, then our knowledge of the universe remains incomplete in ways that cannot be remedied through additional observation or theoretical development. We can calculate, predict, and explain an enormous range of phenomena with remarkable precision. But the ultimate nature of existence, whether bounded or boundless, may lie permanently beyond our cognitive and observational horizons. The physicist Max Tegmark has proposed that all mathematical structures have physical existence, somewhere in a vast mathematical multiverse. In this view, infinity is not just mathematically real, but physically instantiated in unlimited forms throughout levels of reality beyond our observation. Every possible mathematics, including those involving infinite quantities of every type, would correspond to some physical existence somewhere in the multiverse ensemble. This proposal cannot be tested with current scientific methods. It may never be testable through any method humans could devise, but it represents one attempt to take seriously what mathematics seems to be telling us about the structure of reality. If mathematics is the language of physics, and mathematics speaks fluently about infinity, handles infinite quantities with rigorous precision, and finds infinity indispensable for describing the physical world, perhaps infinity is more than human inability to find edges. Perhaps infinity genuinely exists, and mathematics is revealing its structure. You exist within a cosmos that may extend infinitely in space, stretching forever in every direction without boundary or wall. It may extend infinitely in time, with no first moment in the past, and no last moment in the future. It may contain infinite values at singular points throughout its structure, regions where physical quantities genuinely have no upper bound. Your brain, evolved for tracking finite quantities on finite savannas, cannot truly comprehend any of these possibilities, but physics and mathematics point persistently toward the boundless, the endless, the infinite. We are finite creatures grasping at infinite reality. Our equations speak of quantities that have no end. Our telescopes reveal structures that may extend forever beyond our observational limits. Our theories break down at precisely the points where infinity seems to emerge from the mathematics, as if infinity itself resists our attempts to comprehend it. Whether these infinities represent features of reality or limitations of our theories remains perhaps the deepest open question in physics, a question that may define the boundary between what humans can know and what lies permanently beyond us. What we can say with certainty is that infinity is not merely a mathematical abstraction used for calculational convenience. It is a genuine possibility that physics takes seriously, that observations support, and that may describe the actual structure of the cosmos we inhabit. The idea our brains cannot process may be the most accurate description of the universe available to any description at all. And so we find ourselves in a strange and humbling position. Evolved primates on a tiny rock, using brains designed for counting small quantities of berries and predators, have discovered through mathematics and observation that they exist within something that may have no limits. We cannot comprehend infinity. The neural architecture that served our ancestors so well on finite planes fails catastrophically when applied to the boundless. But we have learned that infinity may be where we live. This is perhaps the deepest truth that cosmology reveals about our situation in existence. The incomprehensible is real. The boundless exists, and we are inside it. Finite minds awakening to infinite reality, grasping at eternity with tools designed for counting to 10.